that, it's not always that you will only have a differential equation of first order. You can have one order, second order, third order, fourth order, and so on, right? So that means how to solve this higher order differential equation, the technique should be known to us. So we may not be doing too many problems, because if you go into too many problems, we won't be able to finish our syllabus. But then the techniques which are there, which are needed, I will just give you a brief on that. Okay, linear higher order differential equation, okay, with constant coefficient. Now this is important. We are not going to shift much from here. If you are doing an MSc in maths, probably you will go further with this, but we are going to stop here. Constant coefficient, that's an important term. Okay, so in general, if you just write down an higher order differential equation, it won't be just dy dx, it will be of some order. Let's say order is n, so dn dx n, then plus coefficient is constant, so maybe I can take a coefficient a1, which is actually a constant, so it will be the next order. So whenever we are actually going to write down the differential equation, we are going to arrange it in this descending order of magnitude of the orders of the differential. So maybe I can write down a2 and then dn minus 2 y. There is a pattern here, so we need to just take care of that. Okay, and then finally I can actually have an, and then the final term would be just y. So this is equal to q. So you can have some value on this side. Okay, and if I actually want to find out the solution of such equation, I'm just giving you the general form. Okay, if you know the technique, you can actually use it and basically find out the solution. So if you want to find out the general solution, let's say we are solving it for y would be equal to something which we call as the complementary function. So we are going to see how we are going to find out complementary function. So from now onwards, I'll just write down it as CF. Okay, plus you can actually find out the particular integral, and this entire thing will actually give you the solution and find out the value of y. Particular integral. This is only for higher order differential equation. Even if you do it for the first order also, you see you will get the same answer. Okay, but then there is no use for doing it for the first order. Okay, there are certain forms that we should actually know for this particular expression. So one is actually called the symbolic form. Okay, symbolic form. So in symbolic form, what happens is whatever is the differential d and dxn, I will just write it as capital D to the power n. You might have come across this, but this is actually termed as differential form. A1 is the coefficient dn minus 1 plus a2 dn minus 2, and then I can just take it, write it as an. So what I take common is y. Okay, and then when I write it down on the other side, I will put it as 0. Okay, I will try to make this side, this is a value we have. So we're going to look into problems and going to be more clear. This q, I'm just going to put it as 0. That is actually called the differential form. Okay, and whenever I write down d, it simply means it's d dx. Okay, so in general, if I write it down something as d to the power n, this will be d to the power n dx to the power n. So this is actually how we solve the find out the solution. Okay, the aim is to actually know how do I find out complementary function, how do I find out particular integral, and so on. Okay, so we're going to do that. That's the main aim. Okay, but we are just going to look into different types of writing down the equation, and then we are going to proceed with the problem. And there is something which is called auxiliary equation, and in this auxiliary equation, okay, we are going to just replace this capital D with some parameter or some variable, or we also call it as the characteristic equation. These terms are important, you should remember. Characteristic equation. Okay, and how do I write it down? I write it down in simple. In place of D, I will put a value, any variable m, let's say mn, plus a1 mn minus 1 plus a2 mn minus 2 plus an, and then I'll just equate it with 0. That's it. I won't put a y there. I'll just equate everything with a 0, and you'll be getting an equation, equate it with 0, you solve it and you will get different values of m. Okay, if it's a first order equation, you'll get one value, second order, two value, and so on. So a1, a2 all are constants. Okay, so it will be easy. So this is the first thing that we should know before we actually solve and try to understand how to find out the complementary function. Okay, very important. Okay, so let's just look into certain rules to find out the complementary function. So whenever I write down CF, understand that this is actually complementary function. So what are the rules here? Okay, rules to find complementary function. Okay, so this is important. So let's see how do we do it. There can be different kinds of complementary function. Okay, so what we do is usually we write down the function. Let's say write it down again, a1 d n minus 1, and then a2 dn minus 2 plus, and so on, right, into an into y is equal to, okay, 0. Okay, let me write it down in 0 form. Okay, we'll take this later. And then we can actually have the auxiliary equation. Auxiliary equation for this would be mn, just repeating the same thing, mn minus 1 plus an, I'll equate it with 0. Okay, so we just take this as number 1, and then what we do is we solve for 1. This is the rule. Okay, I'm just writing it down in general so that all of you know how to do it. We solve equation 1. Okay, and for m, we solve for m and get, so it's an equation of order n, so we get n coefficients. Okay, or we can get basically n equation or n roots. Let's say write down n roots. Yeah, obviously. So if it's a second order equation, you are going to get 2 roots, third order 3 roots. So whatever is the order of n, you are going to get that many roots. Okay, whatever the values. So this is what we do with the rules. Okay, and if we just see, when we actually solve it, the values of m, it might be real, it might be imaginary, okay, or it might be a combination of both. Okay, so we're just going to look into 3 cases here. So let's just look into case 1. Okay, roots are real and distinct. Okay, roots are real and distinct. By distinct, I mean there are 2 different roots. It might be there are 2 roots and the values are same, so they are not distinct, right? So in that case, if you want to write down the complementary function, the complementary function would be nothing but c1 e to the power m1x plus c2 e to the power m2x plus cn e to the power mnx. Okay, so just by writing this, maybe you'll get confused. Let me just take a value here. Okay, and give you an example. So suppose you are doing a problem, you are doing a numerical. Okay, and then you have reached at this stage where you can actually write down the value of d in capital D, write down the form of the capital D. So d square minus 3d plus 2, let's say, okay, into y is equal to 0. So you have this equation. If you want to write down the auxiliary equation for this, you can just simply write it down as m square minus 3m plus 2 is equal to 0. And from here you can use the determinant form, or not determinant form, the quadratic form, okay, equation, quadratic solution, or you can actually split the middle term and solve it, right? And then if you split the middle term, I think it is m minus 1 and m minus 2 is equal to 0. And from here you can easily say that the solution for this is m is equal to 1 or 2. So there are 2 distinct solutions. So therefore, for such form, if you want to write down the complementary function, it's very simple, right? It is c1, so c1 will be there, c1 will remain. Okay, we have a constant there, c1 e to the power m1x. So m1 is 1, so I'll just put it as x, plus c2 e to the power m2x. m2 is 2, so I'll write down e to the power 2x. This is your complementary function. Now remember, it's a second order equation, so you have just got two terms here. Third order, you'll have three terms and so on. Okay, so it'll keep on continuing that way. So this is your case 1. Okay, so there can be other cases also. Let me just discuss those other cases first. Okay, so let me just take case 2 here. Case 2. In case 2, what happens is, we have the roots, okay, they are real but equal. Okay, they are not distinct, they are equal. Okay, so in general we can say that this is m1 is equal to m2. It may be that all the roots are not equal, few of them are equal, so maybe m1 plus m2 is equal to m. So now if I want to write down the complementary function, it should be for the equal ones, c1 plus, this is very important, okay, c2x e to the power mx, just one root there for both the cases, plus, and then you can actually have the other ones, e to the power m3x. This is the general form, plus cn e to the power mnx. Okay, let's take an example here for this case. So maybe I can have d square minus 4d plus 4 y is equal to 0, and then if we just solve it, okay, you know, this is d minus 2d into y, okay, and so into, yeah, so it will be a square minus 2ab plus b square. So you can actually have an extension here. So if I write down the auxiliary equation, this will be m square minus 4m plus 4 is equal to 0, auxiliary equation, and if I solve it, this will be m minus 2 whole square is equal to 0. So that means it's a square, so I'll have m is equal to 2, 2. Okay, there are two solutions, but both are same, both are equal, right? So there is no other third solution, so there won't be any c3 term. So if I just want to write down the complementary function for this, this would be c1 plus c2x e to the power 2x, right? So you see this m is 2 here, and we have written it as c1 plus c2x. So don't mix up here, it's not c1 plus c2 bracket e to the power mx, it is c1 plus c2 into x is there. Okay, so you have to take care that you don't mix it up there, that's important again. And then the final case would be imaginary. Okay, so case 3, we are actually going to have roots are imaginary. Roots are imaginary. Okay, so in that case you can write down m1 is equal to alpha plus I beta, and maybe m2 is equal to alpha plus I beta minus, sorry, I and beta is actually coefficient of whatever is the imaginary part, right? Simple, minus I beta. And in this particular case we have got the complementary function as e to the power alpha x. This is again important, all three of them you should remember, cos of beta x plus c2 sine of beta x, right? This is the solution for this. Okay, let's take an example for this now. D square minus d plus 4 is equal to 0. Auxiliary equation is m square minus m plus 4 is equal to 0. Want to solve it, you can actually, you know, use the quadratic equation form. Minus b, b is minus 1, so it will be plus 1, plus minus root over b square means 1, minus 4, a, 4 into 1, a, c is 4, 4 into 4, 16, divided by 2 times of a, so 2 into 1. So if I take this, this would be half plus minus, this is root 15, root minus 15, so that means I can just simply write it down as root 15 into I divided by 2. So in that way I can say that this is my alpha and this is my beta. So I've solved it, I've got the differential form, the roots of the equation, and then I can just simply write it down, e to the power alpha. So alpha is half in my case, so in this case it is half of x plus minus, and then we can write down c1 cos of beta is root 15 divided by 2, don't include I, plus c2 sine of root 15 by 2 into x. So this is the general overview of how you actually solve linear differential equation of higher order with constant coefficient.